Okay.
5 minutes in penalty.
Very good. So let me introduce Sebastiano Corli. Corli.
Yes.
Who's going to talk about solving Rubik's Cube via quantum mechanics and deep reinforcement learning.
Okay. Good morning, everyone. I'm a PhD student with Enrico Prati. So we are talking about this issue for today. Well, let's say that reinforcement learning has been applied in many fields. For example, about finding and solving problems of combinatorial optimization. For example, a great result, a great achievement by the Google team of DeepMind is finding the native configuration for proteins, but the reinforcement learning has been applied for example, for solving the Rubik's Cube and even for the traveling salesman problem. And let's say that Rubik's Cube and protein folding share a common point, a common issue, that is we have so many possible states, many possible configurations, but only one solved configuration. So our approach consists of, first of all, quantizing the cube, and in the second place, introducing some Hamiltonian operators which define a metric that is a distance between any of these configurations and the solved configuration. So let's start talking a little bit about the cube. We have 26 little cubes or cubies. 6 of them are fixed, displaying only one face. 12 are edges, which means they display 2 faces, and 8 are corners, so they display, as you see, 3 possible faces. And there are 2 fundamental features about the cubies, which is the first one, the position, that is how a cube is positioned in the grid of the cube. And the second one is the orientation, that is being fixed at its own position, how the faces of the cube are set. So these features, these observables, are affected by the transformations from the Rubik's group, given by 6 generators and reversed elements. And so we see, for example, we are affecting the position of a cube and its orientation, thinking the orientation as an arrow pointing in some direction. So, fixing the problem, the starting problem, is, first of all, we must say that corners and edges cannot be mingled. They live in separated systems, in separated spaces. They do not interact each other with. And in the second place, we define a starting orientation, an orientation for the solved configuration, as we see in the figure for corners and edges, the little arrows you see in green. And in the third place, we fix a system of axes, spatial axes, the x, y, z, and therefore the quantization, which is we define the 2 observables, which is the orientation and the position for the cubes. These form a complete set of observables, and therefore they commute each other with. That's how to describe a cube, a little cube from the Rubik's cube. And so we go. For describing the orientation of the edges, we have 2 possible outcomes, and so we make usage of a fermion formalism. So an edge can be described as a fermion with 2 possible outcomes of orientation, of spin, let's say. And therefore the corners, we have 3 possible outcomes, as in figure, and so we have 3 possible states, as you see here, and therefore corners can be associated with bosons. And so here a figure about how to see the Rubik's Cube from the perspective of orientation. The blue faces are the oriented one, and the white ones are the not oriented one. With some operators we can swap the white and the blue faces for the edges, or rotate clockwise or anti-clockwise the faces for the corners, and therefore we can observe in which state edges and corner are located for the orientation. And therefore the position of the cube is, so we can perform some kind of translations. For example, we fixed some axes before, and let's say that when rotating a layer, a face, for example the red one, we have some quantic numbers n, which are raising or lowering, going up or going down along a certain axis. And the number which fixes the position of the cube is k, and k is proportional to a vector of integers n, so n k is quite a little bit the same. And here x is just a mute variable to introduce an ansatz, which is the ansatz of the free particle wave function, and the translation operator is nothing but adding some phase at this wave function. And so we go for the edges. Is a little bit more tricky because we are moving along a diagonal direction, but the principle is just the same. Some math properties, for example, as everyone knows, this function can be decomposed into 3 separated functions. Each of them is squarable integrable, and so we can define a scalar product. But most interesting thing is that we can describe the cube, the Rubik's cube, as a multi-particle system, 12 edges and 8 corners, as you see with the spins here, or in the spinal formalism in this kind of fashion. We need to label the cubes from the Rubik's cube, as we see here, and red numbers are the numbers showing the oriented faces. And let's say that when we rotate, for example, the red face, we're moving 1 to 9, 9 to 5, and so on, 16 to 18, and so on. So we need to introduce some permutations, as we see here. And thereafter, we have all we need to implement an element from Rubik's group. As we see here, for example, front face, permutations, translations, and swapping the faces for the edges, and quite the same for the corners. So, some interesting properties, which are these operators can be decomposed into a edge and a corner components. Rotating 4 times with the cube, as here, returns the identity, and even in this formalism it does work. And the most interesting thing is that the inverse of these operators matches with its own conjugated and transposed. That is, this group can be represented as unitary. Here is the sketch of proof 1, 2, composing the edge with its conjugated and transposed. It returns the identity. It's quite amazing. So, we have described how to quantize Rubik's cube. So we need to introduce the metric, the Hamiltonian models. And to do that, we introduced some the Ising model and the Potts model. Potts model is nothing but the Ising model, but with 3 possible outcomes instead of 2. And to describe, to make the orientations to interact, but even to make the positions to interact. And the point is we have 4 Hamiltonians. The first one for the orientation of the corners, the second one for the orientation of the edges, and so on for the position of the corner and the edges. And the overall Hamiltonian has an interesting property, that is, it does exist only one ground state, which matches the solved state of the cube. So, let's say that finding the ground state of the overall Hamiltonian is a very hard task. And the problem was, can we solve each single Hamiltonian, which means finding the ground state for each of these Hamiltonians, and thereafter going to find the ground state of the next without affecting the ground state of the previous one, which means we found the ground state of this. Can we go to find the ground state of the next without moving away from the ground state of the previous one? The answer is yes, because of the group symmetries from Rubik's group. For example, let's say here we have a subgroup from Rubik's group. This subgroup preserves the orientation of the cube. For example, moving 1 time the front face, it means to disorient the cube, but moving twice, of course, it's not solved, but it's oriented, and that's cool. That's how to find the ground state of each Hamiltonian without affecting the previous results. A little bit about reinforcement learning. So here we have the agent interacting with the environment, and the environment in this case is the cube, and the state of the environment is, of course, state of the cube. The actions the agent can take are the the moves, the elements from Rubik's group. And the reward is the metric we were defining before. That is how it means how the agent is going to perform, well or bad. We don't know, but with the reward we can know that. And of course, the reward is negative, but is 0 when we found the ground state. A little bit about how to implement all of this, of course, through a neural network. It's a feed for one neural network. Here we have the inputs. We need to define each of the processes, the 4 processes, to find the ground state of a Hamiltonian. These are the hidden layers where the information is processed, and as an output we have an action the agent must take to find the solved configuration. A little bit of parameters for technical parameters. And at last, our result, that is, we have 94% of asymptotic solutions. What does it mean? Sorry, it means that scrambling the cube, which means moving the cube, inducing a random moves by 10, 12, 20, 30, and so on. At last, we have a kind of asymptotic solution. These are the solutions from how to find the ground state of each of the Hamiltonians. Just to end, if you want to see how we implemented the environment for the Rubik's Cube in a quantum fashion, here we have the link for the GitHub, and that's the paper where we published all the results. And I think I finished for this.
Thank you, Sebastiano. Thank you, Sebastiano, very much for your talk. The floor is open for questions.
I have one comment about an expression. You said quantize is not quantize, but quantify is something completely different. One. 2, I would like to understand where starts the computation, which is artificial AI, because all the first part is how to say is how to write down the system to feed the machine, and that is not artificial intelligence.
No, that's simply having a model.
It's to work, yes. And then now when the machine starts.
Yeah.
And also about the word quantization is not quantization. Is at the most quantifying. It's completely different.
Well, let's say we describe the cube as a multi-particle system, and we define the Rubik's cube as the Rubik's group as a unit in a unitary fashion. So I think we can treat it as a.
But it's just mathematics. It's classical mathematics.
Yeah, of course, but it's
not. No. But it's very important. I mean.
Okay, one, two. Let's say when, for example, one day it can be implemented in a D-Wave and being solved on a quantum computer.
But it's okay. Quantum computer is another discussion. This is classical. All of it is classical. It's not quantization. It's quantifying how to deal in group theory with the cube.
But let's say if we want to talk about sci-fi, we can say that we can construct a superposition for the cube and try to find out if there exists a solution from this. But yeah, of course.
But that is not. There is nothing quantum there.
Okay, you say so.
No, I am not the one saying so. I mean, there is no. It's objective. There is nothing, no action comparable to Planck structure. That is classical. It's group theory. There is nothing quantum.
Okay.
And then the other question: when the machine?
Okay, yeah, of course. Sorry about that. Let's say that, as we say, we have quantified the Rubik's cube, and so we have, as we said, some parameters. For example, this case and the state of orientation for the spins, and just we introduce the feed-forward neural network. Here we take the parameters, we elaborate the information, and we have the output, which is the action. And that's it. That's how reinforcement learning and deep reinforcement learning works with these boundaries.
Thank you.
Sorry. Yeah, I have a question. So you say you want to find the ground state. Maybe I'm just misunderstanding your approach. But so you want to find the ground state. I mean, we know the ground state that you literally had it in your hand. So what I would say, what you want to know is the unitary transformation that brings you from the initial state to.
Yeah.
So do you get that?
Yeah, of course. It's how we solved it. The point is, we instead of solving just the whole Hamiltonian, using the whole Hamiltonian as the metric of the system, we introduced the 4 Hamiltonians, and we solved each Hamiltonian per time, and with using Rubik's the group symmetry from Rubik's group to find the first ground state, thereafter the second ground state without affecting the previous one. So
you get all the...
we go down and down until we reach the overall ground state, which is the soft configuration of the cube.
Just to a little comment to Giuseppe's question. I mean, once you have a Hamiltonian that acts on a Hilbert space, you could, of course, try to find new operators that do not commute with the positions of that measure the positions of the cube. Then you could call it more quantum in Giuseppe's sense.
No,
why
because
not?
we have only a non-commutative algebra.
Sure, but you
That's
have
it.
then
It's
operators that are not commuting. What is different from quantum mechanics?
It's different.
What?
No, okay. No,
What
okay.
is
So this is to clarify for everybody. I call quantum when I have an observable which is comparable to Planck constant. That is finished. Only those systems are quantum systems. But I am not a quantum system.
But
The language is
Planck's constant is just a unit. It's just a unit. So the only thing it tells you is position and momentum do not commute. Otherwise, it's just a unit.
With respect, I think we have to continue with...